All right, thanks, Elba. Thanks, everyone, for sticking with me until the end. All right, so let me again, since it was so long ago that I was talking to you, let me remind you that this morning we talked about tropical Hurwitz numbers. And at the end of the day, what this is a combinatorial algorithm to compute double Hurwitz numbers, right, in terms of a weighted sum of trivalent graphs. And the goal of the next hour, besides getting to the end of the day and then going all to rest and drink beer, right, is to give a geometric interpretation of this algorithm as computing an intersection number in the logarithmic Chow ring of MG and bar. And if you don't know what the logarithmic Chow ring of MG and bar, don't worry about it, because maybe the most important goal of the hour is to make friends with this quantity. Okay? Great. So let me start by giving an introduction to logarithmic geometry. And again, this is meant for non-log geometers, right? So it's in a very simplified setting. It's going to probably contain a lot of things that are not quite fully right, but I think that if somebody wants to drive log geometry, this is a good intuition to have in mind. And so the intuition that for me works is to think of log geometry as a generalization of toric geometry. Okay? And now, we all know in log, oh, and you're not supposed to be able to read this here. Oops. This is for me to write something on the board, right? So don't worry about squinting. So I've put like a big picture with some of our favorite images from mathematics, right? This is P2, right? This is the fan of P2. This is the blow up of P2 at a point, and this is the fan of the blow up of P2 at a point, right? And this picture wants to illustrate the things about toric geometry that I want you to keep in mind, right? We all know toric geometry one way or another, right? Some of us more than others, but we've all encountered P2, right? But even if you've never taken a formal course in toric geometry, these are the few aspects that I want you to, keep in mind as we discuss then this generalization, right? So the first thing is that toric varieties are stratified, right? There's a stratification. What does it mean? We have an interior, which is an open set, which is isomorphic to a torus, right? And then we have a boundary, right, which is a complement of interior, which is then further broken up as a disjoint union of locally closed subvarieties, which are the torus orbit. And stratified further, you even right? So in P2, right, we have our interior where the three homogeneous coordinates are all different from 0, right? And then we have three torus invariant lines with one of the homogeneous coordinates equal to 0, and three torus fixed points where two of the homogeneous coordinates are equal to 0. Okay? Great. So the next thing that, again, I didn't think about for a long time about toric varieties, but one thing that toric varieties have, all toric varieties have, because of the fact that their interior is isomorphic to a torus, is that there is a global notion of monomial rational functions, right? There's right? If you're fancy, you can immediately say, okay, these are nothing but the character of the torus. Great, but if you're not fancy, pick an isomorphism of the torus with some c star to the n, and then you have coordinates, and then monomial rational functions really means xi to the ni divided by xj to the mj, right? Or some monomials in the xi's divided by some monomials in the xj, right? And this monomial rational functions have the property that they're invertible, they're multiplicatively invertible in the interior of the toric variety. They only vanish or have poles along the boundaries. Now, if instead of wanting to say something global, you want to say something local about you put yourself at any point in the toric variety, possibly on some orbit, right? Then you have a local notion of monomial regular functions. You know which one of these global rational functions are actually non-infinity in a neighborhood of that point, right? So we have a local of regular monomial functions. Okay. And this local notion of regular monomial function allows you for every stratum of your toric variety to construct a cone, right? So why? Because these monomial functions form a monoid under multiplication, right? And monoids in a natural way give rise to cone. And shoving something under the rug because really it's the dual cone, the cone that we care about, but you know. So this notion, so 3 gives for each orbit a cone, and these cones come with an integral lattice, with an integral structure. Right? Why? Because I mean these monomial functions have exponents that are integral, right? And so that's an important structure. Again, we're really thinking about the dual cones, but this integrality continues, right? And so then, again, these cones, or rather the duals of these cones, the duals of the cones of these regular monomial functions assemble themselves to give a fan, the fan of the toric variety, X sigma. Okay. And 6, there is, at this point, more or less tautologically from what I said, but there is an orbit cone correspondence, i.e. a bijection between the cones of the fan and the strata in the stratification of the toric variety by torus orbits, right? Which respects or reverses depending on whether you want to put yourself how you define the order, right? But let me say respects the poset structure for the two stratifications. Huh? The fan, I call it X sub sigma. No, oh, sorry, the fan is sigma. Oh boy, yes, thank you. I mean, it's just a name, but it would be a weird name. X sigma is the toric variety. Yes, thank you. The fan is sigma. Again, and again, if we look at P2, right, we have 3 fixed points in P2. We have 3 two-dimensional cones on the fan, right? And if a torus invariant line contains 2 of these points, right, then the corresponding ray is adjacent to the 2 corresponding two-dimensional cones, right? This is important thing. Great. More things about toric geometry I want you to hold into, sorry. in your mind is, and yeah, you might want to leave the lights on for the next few minutes because maybe this is more important than the pictures, is that maps of toric varieties somehow correspond to maps of fans. And of course, what I mean is good maps, right? Of course, you can find some maps from P2 to P2, some rational function from P2 to P2 that are, have nothing to do with the fan structure. But if you want maps in the category of toric variety, so they need to be torus equivariant maps, right? Then they correspond to maps of fans. And in particular, among these special maps, sort of subdivisions of cones, right, correspond to sort of blow-ups of orbits. And again, this is a somewhat imprecise statement because there's only certain subdivision, they're honest blow-ups, some others going to be weighted blow-ups, but in general, some subdivisions of cones will correspond to some irrational modifications of the toric variety. And again, I've illustrated it here, right? So blowing up P2 at a point corresponds to sort of adding this ray to the fan and splitting these two-dimensional cones into two-dimensional cones and adding one ray, which corresponds to a codimension 1 orbit, right? So that's, and there's a precise recipe to do this. And we're almost done to review our semester course in toric geometry, right? So we'll get to 10, right? 9 is that because the interior, a torus, has sort of no intersection theory, right? The Chow ring of the torus consists of only the constants, and it's only spanned by the fundamental class. There's no interesting close-up varieties of a torus. They can all be sent off to infinity and made to disappear, right? Except the fundamental class that cannot disappear. This implies that the intersection theory of any toric variety is completely captured by the boundary. So the torus invariant cycles generate the Chow ring, right? So intersection A star of X sigma, let me say, is captured by boundary. Right? Of course, I could say something more precise, like generated by boundary divisors, but And the last thing is maybe the only thing which is a little bit sophisticated that I'm gonna say and use, but all these 9 points, I think we can all, not be shocked, right? You could all be saying, why are you telling this to us? We've known this since 2nd grade, right? The last thing is maybe a little bit more involved, but is the following statement that the equivariant cohomology of a toric variety, through this theorem of Atiyah-Bott localization, can be identified with piecewise polynomial functions on the fan, on sigma. Okay? We might all have seen maybe the fact that divisors become piecewise linear functions because the torus invariant divisor is a linear combination of boundary strata. Every boundary strata corresponds to a ray. Construct a piecewise linear function, has slope given to the coefficient of the divisor along that torus invariant divisor on the ray, and voila, right? So that's how it works. But this actually generalizes to capture all of torus equivariant cohomology. The price to pay is that you have to consider not just piecewise linear, but piecewise polynomial, continuous piecewise polynomial functions. And the torus equivariant cohomology of a toric variety, by some standard stacking nonsense, you can interpret it, if you want, as the cohomology, the ordinary cohomology of a stack quotient, this stack that you obtain by quotienting out the toric variety by its torus. Okay? This is a weird stack, right? It has one zero-dimensional point corresponding to the torus and a bunch of negative dimensional points corresponding to the orbits, right? They become more and more negative dimensional the more stabilizer you have, but whatever. Some people like it that way, right? There's stackers in this world. Okay. Okay. So at this level, my goal is to sort of like give an intuition about log geometry. These are all things that are more or less true on the nose if x is smooth. They can be modified to hold in some sense if x is singular, but that's beyond what my goal is right now. So, you know, but is everybody happy with all this stuff, right? Because if you're happy with this stuff, I think I can make you at least accept log geometry, right? Maybe not like it, but accept it, right? So my next slide is about, you know, log geometry and how does log geometry, in a sense, generalize. Yeah, do you want to? Yeah, even though I'm still gonna write, but yeah, let's spend a second. Let's spend a second to look at the picture, and then I'll go back to crossing things out there, right? So the example that I want to talk about, you know, log geometry is instead of P2, and I have M bar 1, 2, right? The moduli space of genus 1 curves with 2 mark points, which we've described in the tropical setting in the morning, and M bar 1, 2, which I've copied it twice, because let's start by looking at it down here, right? It comes with a stratification. It comes with a stratification by topological type of the curves parameterized, right? And so it has an interior that corresponds to smooth curves. And then it has strata corresponding to nodal curve, and the codimension of each strata corresponds to how many nodes you have, right? And so there is a natural sort of normal crossing stratification, just like toric varieties. And this stratification can be given, can induce this notion of a log structure, a divisorial log structure, which basically means caring about the order of vanishing of functions that only vanish or become zero along these divisors, right? But again, the way, actually, let me start here. Let me start modifying what I've written so I also slow myself down a little bit. So let me get red for what doesn't work anymore, and green for what works, right? So we still have a stratification, okay? The interior is still an open set, which is certainly no longer necessarily isomorphic to a torus. And we have a boundary, which is now no longer given by torus orbits, but it's, you know, the boundary stratification is given by what are called characteristic monoids of the log structure. And I haven't said what characteristic monoids of the log structure are, but this comes from this next kind of 2 points, right? So we no longer have a global notion of monomial rational function. This we lose. But if we have a stratification, we have a local notion of regular monomial functions, which are namely, you know, if you're sitting at a point on some stratum, are these points, are these functions that are regular in an open set around this point and invertible on the complement of that stratum. To behave exactly like monomials did, right? And so once you have this local notion of regular monomial functions, this gives rise to a sort of a monoid, the monoid of these regular monomial functions. This notion of monoids is now local, and so if you want to make it global, you have to consider a sheaf of monoids. That's why when you open the first page of a log geometry paper, you get hit in the head with this absurd definition that says a log scheme is a ring space with an addition, a sheaf of monoids, yada, 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 and you have no idea what they're doing, but that's what they're trying to do, or, you know, they're doing probably a lot more, but that's what I understand for my purposes. And, you know, because you have this local notion of regular monomial function, you have these monomials, then you get these cones with an integral structure. And you get dual cones that assembles themselves to give a fan. Sorry, not a fan, a cone complex. Okay, because one thing that I had written in my notes, but then I decided to not write, but maybe I should have written, is, let me write it now, in toric varieties, because of these global notions of monomial rational functions, all cones naturally live in the same vector space. Right? All cones live in the character, all cones that correspond to the function live in the character vector space of the torus. All dual cones live in the co-character vector space. And so then when you assemble this cone together, they give you a fan, they give you something that, a collection of cones glued along faces inside a vector space. Now, in this case, we lose this global structure, so the cones do no longer live in this vector space. There are an abstract cone complex. They're a collection of cones together with some face inclusions because, the faces of the cones will naturally sort of have integral structure that agrees with the structure of the interior of the cone. Okay? There is an orbit cone correspondence that is sort of, in a sense, we almost hardwired in. Okay? And now, maps of log schemes. If you have a map of log scheme, which whatever that is going to be something which is compatible with this structure of this sheaf of monoids, of these local rational functions. Now they're not completely determined by map of fans, but they give rise to map of fans, right? So this we save this direction. In general, we don't necessarily, if you give me a map of fan, I cannot necessarily reconstruct and get a map of log schemes, but except when we're very fortunate. Yes, map of, yeah, of course. But there are some very lucky situations in which we can go backwards, and this is the case of subdivision of cones. And in that case, I mean, we're going backwards because if you subdivide a single cone, on a single cone, that single cone can be put in a vector space, and all the action happens in that vector space. So it's a local construction to a neighborhood of the orbit, and so that's okay. And so again, we do retain this notion that subdivision of cones correspond to blob of orbits. It's certainly no longer true that the interior has trivial intersection theory, and it's certainly no longer true that the Chow ring of a log scheme is completely captured by boundary, but part of it is. Oops. But part of it is, and the one that is captured by boundary can be, so let me also get rid of this part. The part that is captured by boundary can be described as the Chow ring of this stack, which now is no longer a global quotient stack of a toric variable torus, but this is called the Artin stack. And this is basically saying, do locally this quotient of, one thing I should say is that this sort of kind of log scheme that I'm introducing are locally looking like toric varieties, so you can do this global quotient locally, and then they patch together to give this stack called the Artin stack. And the cohomology of the Artin stack is, again, naturally given by piecewise polynomial functions on this cone complex, and is no longer equal to the Chow ring of the log scheme, but it certainly admits a morphism to the Chow ring of the log scheme, right? Because the equivariant, oh, sorry. Yeah, it's going this way. sorry, this is, I should have planned this a little bit better. Yeah, let me just erase this t, right? Because again, this is locally an equivariant cohomology, and so it defines kind of a non-equivariant limit to the map, right? Okay. So again, maybe this last point, I've made it more confusing than it needed to be, but what I want to really impress is that there's this combinatorial thing, piecewise polynomial functions on this cone complex that give a map that generally is neither injective nor subjective, but nonetheless is a map to the cohomology or the Chow ring of your log scheme. Okay? And you could argue that, okay, there's people for whom log geometry has other goals and other purposes, right? But for people like me, what you need of log geometry is a theory that allows you to get these things that I boxed in green. These properties. Okay, any questions? Yeah.
You mentioned, I mean, it's constructed by just taking, well, like each cone and looking at the associated torque variety and then kind of gluing it together? Or?
A little bit more complicated than that, but I think, I mean, that's a good start. I mean, if you have any point in the log scheme, which is nice enough, right? Then you can find locally a neighborhood which is et al. Locally isomorphic to toric variety, right? And so there you can construct the Arting fan of that open neighborhood. Then you have this et al. Map, and you have to check if you do it. But essentially, like really, like it matters which orbit you're on, and so you're having these cones. So yeah. Again, I think some real log geometer would like hate me for having said this way, but. Okay. All right. So this was probably the hardest part of the talk. In fact, it took only 20 minutes, right? Now we should start rolling downhill and enjoying things. So yeah, maybe now we're gonna go more on the pictures. So first thing I wanna do, like a little bit, get some comfort about this function, right? So if you know how do piecewise polynomials give you Chow classes, right? Well, I mean, suppose that you have an array in just looking at one particular array inside this cone complex, which has a coordinate x rho. And now you think of x rho as a piecewise linear function on the whole fan by saying it's the piecewise linear function that has slope 1 along this ray and slope 0 along all the other rays. What should it be? Just like in toric geometry, it should be the corresponding divisor. Great. And then if I take powers of this piecewise linear function and get, for example, a piecewise quadratic function, x rho squared, what does it get? Well, that's the square of the divisor, which corresponds to the divisor capped by the Euler class of the normal bundle to the divisor in the space, right? And so if you have this information of these Euler classes, then you actually know what this class is. No, that's additional information that you would need to give. But the map is defined. Right? The map that says this piecewise quadratic function is this class in Chow is perfectly well defined. It's just that you might not be able to read it from the combinatorics. Right? Similarly, now let me look at a two-dimensional cone, right? And if I take a product of this piecewise linear function x rho 1 times x rho 2, right? So I get a piecewise quadratic function, which is x1, x2 on this two-dimensional part, is 0 along this rays and 0 everywhere else, right? Then what I'm doing, I'm intersecting this cone, so I'm getting the codimension 2 stratum, which is in the intersection of these two divisors, these two distinguished divisors. Okay? And this is all well, unless these two rows, these two rays are the same ray, right? So you have some kind of a pita bread kind of cone, right? In which case it's a little bit more tricky, but it's also kind of cool. So let me show a picture for that, right? So suppose that you have a divisor here in dark blue that has a self-intersection, right? And then you'd like to compute the self-intersection of this divisor with self-intersection, right? So how could you do it? Well, one thing you could do is you could consider the normalization of this divisor, right? So instead of having this curly dark blue thing, I have a non-curly, I have uncurled it away, right? And then you could take the normal bundle, you could pull back the normal cone to this thing and get a normal bundle here. You could get a section of the normal bundle, which means essentially sort of wiggle this thing so it becomes a little bit transversal, and find some intersection points. These are the green intersection points. Then put this, both the zero section and the deformed section of the normal bundle, put it back in the original thing via the normalization morphism. Of course, the green points are there, you see them, but then you get more points, some of these red points, that correspond to where sort of the non-deformed section and deformed section intersect transversely. Because if you think of this as an immersion rather than embedding, the time parameter for the dark blue here is very different from the time parameter for the light blue here. And the trajectories that come there at different points. And so you would not see these red points here, where you're actually seeing the abstract motion, but you'd see them here. And so you have two kinds of intersections that contribute to the self-intersection of this divisor. I like to call them, but this is just the way that I describe it to my grad students to be faster. I like to call these green points the sort of the non-transversal intersections and the red points the transversal intersections. Right? And this piecewise polynomial functions in this case capture exactly these two types of intersections, right? The x1 times x2. If x1 and x2 are the coordinates on this rays, but this ray is the same ray, right? This, twice, to be honest, this thing captures precisely this intersection, whereas the square of the coordinates, which is the thing that generalizes this thing, right, captures the non-transversal part. Okay? So again, I wanted to show this, with some characters to point out, yes, there are subtleties, but one can, learn this yoga and then become pretty comfortable to understand how this piecewise polynomial function give rise to Chow classes. And so then you can start playing the game and say, okay, for the spaces that we care about, like M12 trop, right? Here are some examples, right? If I consider the function sort of y0, where y is the coordinate on this cone, right? X is the coordinate along this ray, and so this function has slope 1 along the green ray, slope 0 along the dark green ray that correspond to this boundary divisor. Vice versa, if I want a function that has slope 1 along this ray and slope 0 along this ray, it better be x on this cone. And because this cone is folded, it has to be sort of symmetric, linear symmetric, well, better be x1 plus x2, and so that's the way that you describe this divisor. And again, maybe let me move on a little bit faster, because these are, again, examples of piecewise quadratic function. These are two codimension 2 strata obtained by intersecting divisors. And this is the example I just talked about, is the transverse part of the self-intersection of the divisor. And this piecewise quadratic function is the non-transverse part of the intersection of this divisor, which can be described in terms of psi classes if you're comfortable with those things. Otherwise, this is modular space of curves, mambo jumbo. So, any questions so far? Okay, so then one possible question that somebody could have asked is like, well, what do you mean by piecewise polynomial exactly? Right? Because piecewise polynomial is things that are polynomial in pieces, and the way that you've done it, you sort of seem to be requiring something a little bit stronger. You seem to be requiring that these pieces must be at least as large as the cones. That all that I've done so far are polynomials, are piecewise polynomials, but on each cone they're honestly polynomials. What if I want to go wild and take this two-dimensional cone and say, oh, well, I want x on this half and y on this half. Which means that now this is a piecewise polynomial function, but the domain of polynomiality, right, breaks this cone into two cones. And so I have, if I look at the cone complex structure induced by the domain of polynomiality of this piecewise polynomial function, I have an additional ray. And this function, this x here and y here, which is also known as minimum of x and y, is now a function that has slope 1 along this ray and 0 along these two. What should it be? Well, if I subdivide a two-dimensional cone with a ray, what I'm being told to do, somewhere here that now I cannot find, here, is I need to blow up the corresponding stratum, right? So I should blow up M12 at this stratum and get an exceptional divisor. This ray corresponds to this exceptional divisor. The piecewise linear function with slope 1 along this ray correspond to this exceptional divisor. Okay. So if you allow the domain of polynomiality, the domains of polynomiality of these piecewise polynomial functions to break the cones, then these don't necessarily give you elements in the Chow ring of the original space, but they give you elements of the Chow ring on some birational model of that space that has a dominant map down to the space. And so, okay, if we want to consider all possible piecewise polynomial functions that break the cones in all possible ways and yada, 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 and want to have a consistent theory, then we better work with the whole directed system of birational modification of MGN bar, obtaining by blowing up orbits or proper transform of orbits or anything that is, not random, not something right in the middle of a stratum, but that behaves well with the log structure. And then we have a directed system. Each of these birational models has a Chow ring, and we can consider the directed limit of all these Chow rings. And we're going to call this the log Chow ring of MGN bar. Okay? And now the statement that needs to be a little bit corrected, right, is that I have a map from piecewise polynomial functions to the log, the log Chow ring of, this is just for whoever comes in late at night, so it's recorded. Nothing is happening interior. And even like along the boundary, if I have a torus invariant line in P2, I'm not allowed to blow up just a point inside this torus invariant line, right? They have to really blow up, either orbits of, again, if you keep going, proper transforms and stuff like that, but things that are sort of orbits, now it's what's going to be the stratification by monoids. Okay, so I've made now something which is complicated, like the Chow ring of the modular space of curves, even more complicated by saying instead of one messy Chow rings, work with a directed system with infinitely many messy Chow rings. Why would we want to do that? And a motivation for that is this thing called the logarithmic double ramification locus. This logarithmic double ramification locus is an element of the log Chow ring of MGN bar. And it's something that is born on the smooth modular space of curves as a locus of curves with n-mark points such that a divisor of the form summation of xi pi is principal. And this is our friend, right? Up until now, I've resisted Jürgen's temptation of tell me how to compactify the space, right? I have not told you how to compact, but that was the space we're looking at in the uncompactified version, right? And so one way to describe this space is that you have MGN. Over this, you have the universal pick GN of degree 0 over it. And we have two well-defined sections of PICGN, the 0 section that assigns to each curve its trivial line bundle, its trivial structure sheaf. And then we have this sigma x, which is the one that depends on the x's that we care about, that every curve assigns the line bundle OC of summation xi pi. And this double ramification locus here amounts to intersecting the image of these two sections here and then pushing forwards, or if you prefer, like pull back, the image of sigma x via 0. But then, of course, doing intersection theory on MGN, terrible idea because space is not proper, you lose a lot of stuff. So you'd like to do it on MGN bar. We have a very natural compactification. Even setting aside the complications of working with a good compactified Jacobian theory, which again it can be done. Margarita is here; she'll do it for you if you're nice to her, right? Even setting that aside, you have this problem that yes, the zero section extends in a natural way, at least so long as you allow the multi-degrees all zero there, but the Abel-Jacobi section will not extend. And just there's no way around it. It does not, it has indeterminacies. How do you resolve indeterminacies? You have to blow up. Okay? And so somehow, these log geometers folks, right, have figured out that, well, depending on the axis, log geometry tells you exactly what you have to blow up so that the Abel-Jacobi section extends. In fact, if I have to be fully honest, this M tilde here where the Abel-Jacobi section extends might be a bunch of blow-ups, and then you throw away something. So this thing is actually not honestly proper if you want to have a finite amount of blow-ups. But it's good enough in the sense that the intersection of the sigma that extends and 0 is proper. And so then you can pull back the image of sigma via 0, and you get something proper downstairs. And so that's what you define the logarithmic double ramification cycle. Okay? And so this is, in a sense, the natural thing, the natural way to compactify this natural locus, but this natural way does not live in MGN bar. And it will live in a different space depending on what the x's are. Okay?
Because you have too many choices.
Yeah.
Where do you find it's just projection formula?
So that's well defined. There is some work that needs to be done. Yeah, but it was done by people bolder and braver and more technically prone than me. But yeah, but you're right. One could worry that if I do a bunch of blowups and you do another bunch of blowups, they resolve the indeterminacy of sigma in different ways. If we then dominate our two blowups, do the two things give the same object? Yes, they do, and this has been proven. And again, one could argue, well, but then once you've constructed this thing here, why don't you just push it back forward to MGN bar and work with this? Yes, you can do that. That's what's known as the double ramification locus, not the log one. But this thing right here ends up not behaving as well as the log one. In the sense that, ask me if you want to know. Okay. All right, so I'm now ready to state a theorem, right? This theorem that myself and Hannah Markvik and Dhruv Ranganathan put out on the archive about, I don't know, 6 months, a year ago, right? Which is, okay, the double Hurwitz number HGX can be computed as an intersection number in the logarithmic Chow ring of MGN bar. And it's an intersection number of this logarithmic double ramification locus with this element of the log Chow ring, which is described as a piecewise polynomial, Bx, which we've called the branch polynomial. But okay, it is a vague statement, but the important thing is that both this branch polynomial and the birational modifications of MGN bar that you need to do this computation are very explicitly determined by the tropical moduli space of covers, right? By these graphs that we talked about this morning. Okay, so let me pause for a second and think, what have we achieved here? We're describing double Hurwitz number as the degree of a zero-dimensional cycle. The ingredients of the zero-dimensional cycle are somewhat natural, or at least as natural as you would think the logarithmic double ramification locus is. But also tropical geometry determines in a very explicit way what these log Chow classes are that you need to intersect. And you need log Chow classes. You cannot do it with classes in MGN bar. Okay, so that's I mean, you could be happy or sad about it, but it's just the way it is. Okay. And again, let me say only a couple of words about the proof and then just sort of show it in an example. Because the proof, in a sense, after all this work is a little bit anticlimactic, because we have this tropical algorithm to compute double Hurwitz numbers, and we can actually define this branch polynomial, this element in the log Chow, so that when you intersect it with the log of dr, it produces precisely this algorithm. So we knew what we wanted to obtain, and we just created so we obtain. Then, of course, this branch polynomial is not some randomly awful thing. It also feels pretty natural, so it feels a little bit better than just kind of reverse engineering a solution, right? But let me show, again, instead of babbling too much, let me show you just one example how this is working, right? So our favorite Hurwitz number this morning was H1 3 minus 3, which was 2, right? So genus 1, degree 3 covers fully ramified over 0 infinity with 2 ramification points. There is a locus of curves in M12 that corresponds to the moduli space of such covers. The thing that this locus does is it behaves badly in at least 2 ways, right? One way is it contains, it's a curve inside a surface, and so you would expect behaving well means a curve inside a stratified surface should intersect the one-dimensional strata of the stratification in points, right? And it should not intersect the zero-dimensional strata, right? If you have a stratified surface and you chuck a curve at random, that's what will happen with probability 1. But this double ramification locus fails on both counts, right? It contains one of the 2 strata, so it spread itself, one of its components spread itself completely on one of the curves, and the other one goes through a zero-dimensional strata. So, and that's the reason why you cannot really cut down this Hurwitz number as an intersection number on M12 bar. So what do? Then we consider our moduli space of tropical covers that in degree 3 consisted of exactly 1 ray. Okay. This ray lives inside M12 with slope 1, 2, right? It corresponded to this little cover, right? And so the length of one edge is twice the length of the other. This ray subdivides this cone. And so it's telling us you need to blow up this point where you have this bad behavior of double ramification locus. Now, because this cone is a folded cone, so there's some stacky nonsense. It looks like one blow up, but they have 2 components. It's chain of 2 P1s. If you look at the fine picture, okay, don't worry about it. But then if you blow up M tilde and now take the proper transformed double ramification locus, well, there's this part here which is unrescuable because that's, but this part becomes dimensionally transverse to the boundary. And so you can hope to obtain the Hurwitz numbers by intersecting this curve with this exceptional divisor. And so, well, how do you do that? Well, we know that the exceptional divisor will correspond to a piecewise linear function with slope 1 along here. We know from the tropical algorithm that we want to count that graph with multiplicity 2 times 1, and so we define the branch polynomial in this case to be the piecewise linear function that has slope 2 along this ray and 0 among all the others. Then when you compute the intersection number in the logarithmic Chow of this piecewise linear function with the dr, what it produces is precisely the tropical algorithm before. And so the kind of nice thing is that this simple process works always. Okay? There are technical subtleties in the sense that if you go to sort of higher dimensions, higher genus than genus 1, then the moduli space of tropical curve is only codimension G inside MG and trop, and so it doesn't automatically subdivide the cones, but then you can choose any way of subdividing the cones that contains that as part of the subdivision, and this will give you potentially many different possible birational transform, but they're all compatible in the sense that if you refine the subdivision, they'll give you the same element log Chow. And so everything sort of works out pretty well. Let me pause for a second, because this is the end of this Hurwitz numbers, and then the next 15 minutes, great. I want to show you like a bunch of other enumerative problems that are similar to Hurwitz numbers that arise once you embrace this point of view, and that I'm really kind of eager to show to this audience because it's a bunch of things that look like they should have structure that somebody should tell me, oh, that explains the universe. Let's write, you know, a paper that says why. Yeah, it's okay.
And compactified, just natural compactification would be just compactified by admissible covers, right? Mm-hmm. Just a closure of the locus in the open space in the closed space. Yeah. And then essentially multiplying by one psi-class at one of these 2 points, you do compute this Hurwitz number.
Yeah.
So why to bother about the rest? So
because we're mathematicians, we like to solve problems in ways that show different kind of stuff. In a sense,
but you see, so the point is the following. So when you define your DR cycle, like using the stable relative maps, you did include something that you wouldn't have if you would just define it by admissible covers.
Yeah.
So you first include an extra stratum that actually spoils all your computation, and then you fight hard with this logarithmic Chow ring to get out of this.
Yeah, but I mean, let me give you an answer that you might or might not like, right? Your approach, right, computes the Hurwitz numbers as a tautological object that has to do with a natural map between the moduli space of admissible covers and the moduli space of branch divisors. Has nothing to do with the moduli space of curves. Okay? So one could say, right, I actually want a computation that happens as close as possible to an intersection theoretic computation on the moduli space of curves, right? Because well, I want to learn something about the moduli space of curves here. For example, I mean, the class of these admissible cover loci is something that we don't know in general in the moduli space of curves. They're very difficult to compute. We can intersect the hell out of things with the admissible cover. Right? I mean, you and I, like, we started our careers doing that. Like, you know, everything that arrived our way, we put it into a cover and compute it. Right? But I mean, unless there's some secret, society, but I'd be very offended to not be invited to the secret society. I don't know the class of many admissible cover loci inside the moduli space of curves, and I would like to. Right? And so, in a sense, I mean, we can chat a little bit more later about my wild dreams that I don't want to say while I'm being recorded because I'll probably embarrass myself. But there are wild dreams that one might actually understand better these admissible cover loci by putting them in some birational modification of the moduli space. That somewhat satisfy you? A little bit. Let's have a drink at some point. And
saying. I don't know what he's saying.
So what Sergey is complaining that I'm working too hard because we have an admissible cover space together with a branch morphism to some m bar 0n if you want or something less, and the Hurwitz number, and there's a comparison theorem between psi classes here and psi classes here. Psi classes are really easy to compute here, and you can compute the Hurwitz number this way. And it's absolutely true, but what I'm saying is that that will give you very little information about how ad sits inside MGNR. And this whole working hard is trying to understand double Hurwitz numbers at this horizontal level without really invoking too much this thing. And so we're this branch upper star of a point, we're working very hard, and I agree, to make it be born as some sort of cycle in the logarithm.
No, but I can actually add to my remark. I mean, you are only interested in intersections of double verification cycle with some maybe, okay, so you use a different class, but in this scheme you can use just product of psi classes, right? Okay, so if it's the case, then the point is that if you look at the intersection numbers of products of psi classes over their cycles, so these numbers are kind of easy to compute. So I mean,
Yeah. I mean, but again, if you embrace this perspective, besides the wild dreams that I have of using these ideas to understand admissible covers, I can actually kind of also come up with new Hurwitz-like enumerative problems with similar structure, like piecewise polynomiality and wall crossing and so on and so forth, that cannot arise from a branch morphism because they come from spaces, the spaces of meromorphic differentials that don't have an honest branch morphism, unless by honest you mean some chain of P1 mod GM stack nonsense, right? So that's the next 13 minutes.
I think the right upshot of your answer is that in this example, the admissible might look more simple, but if you want to have a general answer for any GN, in fact, I mean, the one you started with is more simple, right? So that's probably
I mean,
Yeah, or you should say you get more. So you don't just recover the degrees. Of course, you get a class in the moduli space, so you can pair with other things and so on. And
Yeah. Okay, so
there's advantages.
yeah, so let me, I mean, actually, what I want to show next might or might not help answer some of these questions, right? Because from a tropical perspective, right, there's a lot of modifications that you can do to this combinatorial setup, right? So
Can I ask a quick question?
Yeah.
This double ramification cycle, that is, it's in the image of this piecewise polynomial function.
the double
Can
ramification
you do
locus.
the calculation entirely in the piecewise polynomial?
Yeah, no, it's not.
It's not.
Yeah. It has a part that comes from honestly from the interior, and a part which is the image of this piece of polynomial. The part that comes from the interior for the honest log dr is just in terms of psi classes. There's nothing else, so you can write the dr as a polynomial in psi classes plus something that is completely coming from. I mean, I should not quite say it that way. Something that comes from the piecewise polynomial part, possibly with some psi classes pushed forward. But yeah, but the ingredients are psi classes and piecewise polynomials. But again, from the combinatorial perspective, one thing that we can do is we can tweak the balancing condition, right? And say, what if we, instead of having water flowing through this network of pipes that is conserved from left to right, we understand that each of these joints are old and rusty and start leaking in a prescribed way. So all trivalent vertices will leak one. You can define a combinatorial algorithm. You can compute these numbers that are piecewise polynomials, they have wall crossings, and so on and so forth, right? And do they compute anything geometrically? Right? And again, they compute some intersection numbers in the logarithmic Chow ring of some piecewise polynomial classes, the branch polynomials, with these double ramification cycles at level k, which are sort of some spaces of meromorphic section of the k tensor power of the canonical mantle of the curve. Right? And so there is this natural spaces, the natural geometric loci, that now do not have a classical branch morphism because a section of the canonical does not have a function to P1 is a section of a trivial bundle that has a projection, so it has a map and has a branch morphism. But a section of a canonical does not have a natural loci. Right? And so this is one kind of thing. And so, for example, here's some fun formulas. If we do genus 0, and the one part case, so we have full ramification D on one side, an arbitrary ramification x1 to xn on the other side over infinity. The Hurwitz number is very, very simple. Absolute factorial is just a power of D, right? But if we do the k-leaky Hurwitz numbers, where we do the corresponding number over this moduli spaces of meromorphic pluri-canonical meromorphic sections, then we start getting this sort of this falling factorials, right? Instead of D, you get a product of D minus ik over 2 from 1 to n minus 3. Okay? If nothing else, these are fun things to play with. But then again, if you start liking these things, then you can say, okay, I have this branch polynomial that somehow what it does is forcing my curves to degenerate as much as possible. It breaks my curves so that they cannot break any longer. But I can create some partial branch polynomials that will only degenerate curves a little. For example, here it's a degree 2 branch polynomial where I just allow, basically I want the base curve to have 2 nodes, right? And so then what you get is some graphs that do not satisfy all the conditions. I mean, the vertices are no longer trivalent, but satisfy many of the other conditions. And correspondingly, however, these graphs, right, will give rise to some sort of piecewise linear functions that then you can intersect with some double ramification cycle and this branch polynomial. And then, if you want, you can complete, you have some space to kill, so you can complete it by adding some of your favorite classes. So, for example, psi classes. And so, again, you get this whole set of problems that interpolate between Hurwitz numbers on one side and the Burjak-Shadrin-Spitz-Zvonkin numbers on the other. There are monomials of psi classes in the double ramification cycles. And for all of these problems, let me speed through this because I think we're all getting to the point that we're pretty tired. But for all these problems, you get this sort of combinatorial algorithms in terms of graphs, right? So let me show you, instead of just talking through the algorithm, let's just show you again some weird formulas. If, again, we do genus 0, one part, and now we take the psi class at the fully ramified point, the one on the left, right? Then what happens, remember that before, if E was 0, right, then we had this full falling factorial formula, right? Now we sort of modify it by dividing by some factorial down here, and by not taking all of the falling factorials, but only a part of it. Things get even more fun or complicated if you start putting the psi class not in the fully ramified point. Because now here we don't have an answer yet, but we have, we know that this formula should be polynomial. We can prove that it should be polynomial in the xi's, in k, and in d, right? But, sorry, not in the xi's, but in the x2, right? In the only x that supports the psi class. But we only know that if you specialize to k equals 0, you get something that looks like this. And if you specialize to x2 equals 0, you get something that looks like this. We've been spending a few days really trying to work hard to find something that specializes two ways. And at this point, we still haven't, right? But I mean, I'm hopeful. But if you can guess a formula, then this tropical algorithm, again, they're not efficient to compute, but they efficiently give rise to recursions, kind of like cut and join equations that you can use to prove these formulas if you can guess them, right? And the last variation that I want to mention, because it's in a sense even weirder, is what if you have these partial branch polynomials and now introduce like these lambda classes, lambda j, the Chern classes of the Hodge bundle. And so here what happens is that if you want to compute call these lambda j partial Hurwitz numbers, when I compute these partial Hurwitz numbers, you get, again, some graph algorithm that will compute the lambda j Hurwitz number of genus G in terms of the graphs of genus G minus J. They compute the same Hurwitz numbers. So for example, if we do, let me just say one very special case. If I do lambda G Hurwitz number of genus G, you compute them on trees. And these trees need to get decorated by genus 1 vertices. And then each genus 1 vertex will contribute some 1/24. And then, again, you have a very simple combinatorial algorithm that computes this thing.
So for example, this says, okay, you can organize all lambda twisted Hurwitz number in some jumbo generating function where like you can filter them in completely different ways that you would do classically, because you can say, well, let's filter them by, let's organize them by the genus of the graphs that you compute them with. And that's a new sort of structure that you could give these partition functions that I have no idea if it's useful or useless, because I just compute stuff, right? I like enumerative geometry, but I would be very happy if there were some interesting structure that you can obtain this way. All right, and this is all I wanted to say, so thank you very much.